So, hello everyone. Welcome to the second lecture in the series of special relativity, in particularly four vectors. So in the previous lecture, we have discussed about what are called four vectors, and then we have also discussed that what are the properties for a physical quantity to become a four vector. So let me revise those concepts. So I meant, suppose say a mu stands for 4 vector. Now this can represent any physical quantity. It can be for velocity, it can be for acceleration, it can be for force or for momentum and many more. Or it can be even let's suppose a charge density. Now I said in the previous video that for a particular quantity to be a 4 vector, it must obey two very important rules. The first rule was that it must undergo or it must obey some kind of transformation rule. Now what was the transformation rule? So the transformation rule was, suppose if I am talking about a 4 vector which is represented by a mu, it would be a bar mu which is equal to sum over lambda mu nu, where nu goes from 0 to 3, and this would be a nu, where this parameter lambda mu nu is called the Lorentz boost or the Lorentz matrix. Now this Lorentz boost is represented or is written in the following form. The first term, it is basically a 4 cross 4 matrix. It's a 4 cross 4 matrix. So it can be written as, the first term will be minus gamma, then we have it was gamma, then we had minus gamma multiplied by V upon C, then 0 0, and then we had minus gamma V upon C, then again gamma 0 0, then in the third line we had 0 0 1 0, and then 0 0 0 1. So this is a Lorentz boost, or you can say a Lorentz transformation matrix. Now let me tell you students one very important thing. If I take the determinant, now it is also sometimes represented by a plain lambda. Now students, if I take a determinant of this particular matrix, then the determinant would either give you a value of +1 or it would give you -1. Now please remember it. Sometimes it is also asked in, I believe it was asked in, about 2 years back in CUET PG exam, that what is the determinant of Lorentz boost, and also in an exam from TIFR. Okay, so and the second important rule is that the inner product or the dot product of two 4 vectors must be Lorentz invariant. So what did I say? Suppose I am saying that, let's suppose say that a mu are two 4 vectors. Now if I take the inner product or the so-called dot product of these two 4 vectors, now that must be constant. Now it can also be expressed in the following form: minus a naught square plus a1 square plus a2 square plus a3 square. Now students, please pay attention to this, that in this expression a1, a2 or a3, the powers that you can see over here, 1, 2 and 3, these are not exactly powers, they are basically superscript. This is usually written in 4 dimension, where a1, a2, a3 are representing the 3 spatial coordinate, that is S, P, A, T, I, A, L, or the 3 space coordinates of vector A in 4 dimension, and A naught represents the temporal coordinate. So this is how you are supposed to find the inner product or the dot product of two 4 vectors. Now moving ahead, we will be discussing some important elements or some important types of 4 vectors that we usually encounter in theoretical physics, in particularly in special relativity, or be in particle physics or in high energy physics. So the first 4 vector that we will be discussing is the velocity 4 vector. Velocity 4 vector. Okay, so now let's see what a velocity 4 vector means. Now students, you must know that a velocity 4 vector, it is represented by u mu. Please follow this particular thing. This is very important. Velocity for vector is represented by the letter u mu, where mu is basically an index whose value varies from 0, 1, 2 and 3. It is allowed only the 4 possible values 0, 1, 2 and 3. Now I will explain what would be mu 0. So what would mu 0 mean and what would u1 means, I will explain in a minute. So now, as we know from a very basic knowledge of kinematics, that velocity is basically the rate of change of distance or the displacement. Now using that same logic, I can write that the forward velocity u mu is basically defined as the rate of change of the forward position. Now you see students, x mu represents the forward position upon d tau. Now what did I write? I have written that forward velocity u mu is rate of change of forward position with respect, and in here I am not taking some ordinary time, but here d tau is basically I can say that it is an element of a proper time. Now let me tell you what is d tau. D tau is basically the proper time. It is basically the proper time, right? Now you might wonder, why didn't I take dx mu over dt instead of taking this quantity? Why am I taking dx mu over d tau? Now there is a very important thing. So students, the most important thing that one encounters while while studying relativity, we come across the fact that for every observer the clocks are different. For my let's suppose say I have two observers A and B, and both the observers are observing some event that is occurring somewhere in space. For both the observers, the time that would take for the event to occur, it would be different, right? So when I have written d tau, so this d tau is actually the proper time, and for this reason I am not taking. Now let me tell you what would I mean. I'm saying that we do not take the time with respect to an observer. That is the basic essence of what I am saying. We are not taking the time with respect to an observer. Rather, we are taking the time with respect to the particle of whose forward velocity we are measuring. Because in relativity, every observer has different clocks associated with it. Now, this is a very important aspect of special relativity or in general relativity. Let me remind you once more that we are saying that we are taking d tau, where d tau is a proper time, and that is we are saying that for every observer in relativity, different clocks or different times are associated. So in order to avoid that, we here are defining the forward velocity with respect to the particle, right? Okay, now kindly follow this. Now as students, now as you can see this, what I can do is I can also write this as u mu, which is equal to, if I write it like this, where mu varies from 0, 1, 2, 3, dx naught or dx0 d tau, we have dx1 d tau, then we have dx2 d tau, and then we have dx3 d tau. Am I clear what I am saying? I am basically varying the indices of mu from 0, 1, 2 and 3. Now see what I will be doing. Okay, fine. Now I will be making some changes. Now I believe you have also learned about a formula in time in relativity, that is dt is equal to d tau over 1 minus root over v square upon c square. This can also be written as gamma into d tau, right? Where d tau stands for the proper time and dt is the time with respect to the observer, with whom we are calculating. Here d tau is not the time that is calculated by the observer. Here dt is the time with whom the observer is calculating. So in generally I can say that we have this formula dt is gamma d tau, and from this we can write d tau is 1 upon gamma dt. Now what did I say? Initially I have said that we are defining the forward velocity with respect to the proper time, not some time with respect to some observer, because in relativity every observer has different time associated with it. But here now, as we are performing the experiment, so it would be better that if we convert this proper time d tau into in terms of dt. Did you get what I'm trying to say? I'm saying that usually when we are defining force velocity, we have defined it using the proper time, right? But as we are working with it, so we have to change the time with respect to us, and therefore instead of expressing the force velocity in terms of proper time, we are expressing in with respect to the time that is measured by the observer. So here this formula basically becomes, or you can also rewrite this formula as u mu is gamma dx mu upon dt. So if you take this, then you would definitely have dx0 over dt, dx1 over dt, dx2 over dt, and dx3 over dt. Am I clear? Yes, so as we were saying that the force velocity is now defined, or now it becomes gamma dx naught dt, dx1 dt, dx2 dt, and dx3 dt. Now what we can do is, now as I have already mentioned in the previous video, that we will be following few conventions, and the conventions are that x naught will be representing the time ct, because in Minkowski space, where and in the four vectors, the time will always be written in terms of ct. But now ct is represented by our convention, by our newly introduced convention, that is x naught. The x coordinate will now become x1, the y coordinate will now become x2, and the z coordinate will now become x3. Am I clear? So because we are having dx0, dx1, dx2 and dx3, so we'll try to break this particular thing into the known usual format. So we have this. Now suppose students, if I take differentials both sides, this would become dx0. I mean, I can, instead of giving this, I will be using equal to sign or the equivalent sign, which is basically the same, right? So if I take differential both sides, then dx0 will be giving you dct, dx1 will be giving you dx, dx2 will be giving us dy, and dx3 will give us dz. Am I clear? So now what we'll be doing, we'll be replacing dx0, dx1, dx2 and dx3 as we have obtained over here. So u mu, which is the force velocity, u mu, that becomes gamma, dx0 becomes dct, dt of ct, comma, dx1 becomes dx, dx2 becomes dy, and obviously dx3 becomes dz, and obviously in the denominator we have dt, right? So now what we can do, we can write u mu, which is the force velocity, gamma, and then we can write this as, we can write this as, now you see, c is a constant, so it can be taken out, and then we have d dt of t, which is 1, comma, dx dt is the ordinary velocity which is defined in the Euclidean space. So are you getting my point? Now what I have done, students, is that this u mu, this is the velocity which is defined in the four-dimensional space-time, that is in the Minkowski space-time. However, this dx dt, this dy dt and this dz dt, it is representing the ordinary velocity which we study in the normal Euclidean space or in the Euclidean geometry. So this would become Vx, this would be Vy, and this would be Vz. Now as you can see, students, Vx, Vy and Vz are representing the three components of the velocity along the x, y and the z axis. So now we can also write this as u mu is gamma c comma v vector. So this is the 4 velocity. So you must know that either we can express 4 velocity in terms of this, or we can also express a 4 velocity in terms of this. Both of the expressions are equally important, right? And now what I will be, and students, if you remember that in the beginning of the video I have said that for any physical quantity to be a 4 vector, it must obey 2 important rules. The first rule is that it must obey some transformation rule or the transformation equation, and the second was that it must have the inner product of 2 4 vectors, which is a constant. So my intentions as of now are very clear. My intentions are that I want to check whether this particular entity or this particular quantity u mu, which I am calling as a 4 vector, or which I am calling it as the velocity 4 vector, is it really a 4 vector? Are you getting what I am trying to say? I am saying I have predefined, or I have taken this that u mu is a 4 velocity, and then I have and then I try to obtain the one more form of this 4 velocity. Now what I want to check is that if this u mu, which I have defined as a velocity 4 vector, whether or not this is actually a 4 vector. And in order to test that, we must first obtain the transformation rule, followed by we must also find the so-called the inner product of the 4 vector, right? So let's try to do it.